Great. So now the energy required for the excitation. If we see sigma to sigma star transition, the energy required is quite higher. Followed by we have n to sigma star, which also requires higher amount of energy. And then we have pi to pi star excitation that requires also quite a similar amount of energy. And then we finally have n to pi star transition. So these are four kind of a transition. So increasing order of the energy required in the increasing order, that is nothing but sigma to sigma star. Then we get n to sigma star, followed by pi to pi star and n to pi star. So this is the energy required. So if we know our UV region is not able to give enough energy for the excitation of the sigma to sigma star and n to sigma star. So allowed transition in the UV region, the UV visible region, specifically in the UV region, is the pi to pi star energy transition and the n to pi star transitions. So we should understand what molecules are able to have transition under pi to pi star and n to pi star. As I told earlier, the pi to pi star transition usually happens in the double bonded molecules, that is your sp2 hybridization, sp hybridization, alkenes and alkynes. We also call them at the conjugated bonds, and also some of the functional group. So let's say the absorbance due to pi to pi star transition happens usually in alkenes and carbonyl compounds and alkynes, where exactly n to pi star transition happens in the unsaturated carbonyl compounds. So we usually see the transition happening from the pi to pi star and n to pi star because the energy available for the transition is from 200 to 400 nanometer. If we go below 200 nanometer, let's say 150 nanometer, some of the alkyl halide compounds are able to have electron transition below 200 nanometer, that is 120 nanometer and all those. But usually 200 to 400 nanometer, there are only two transition happens, that is pi to pi star and n to pi star electron transition. And this is the reason, if we see, why we do not need a compound colored in the UV region when we use for the analysis. Like now we'll go by one to one which compounds show the UV visible spectroscopy activity. Now first I have shown here a nucleotides, nothing but consisting of a phosphate group, pentose sugar and a nitrogenous base. Now I told conjugated bonds. So nitrogenous base is nothing but having a benzene ring, that is again having a conjugated bond. So in the DNA, nitrogenous base contributes for the absorption in the UV region. So when we use DNA for the purification or analysis of the purification, usually it is estimated at 260 nanometer without making the DNA to react with the reagent. Here we can directly measure the absorbance of the DNA because the nitrogenous base is able to absorb the UV light at 260 nanometer. Then we going amino acids. The amino acids, only three types of the amino acids are able to absorb the UV region light. That is phenylalanine, tyrosine, and tryptophan. The reason is these have aromatic rings, which is not present in the other amino acids, and these contribute for the absorption approximately at 278 nanometer or 280 nanometer. Then we have here ethylene, 1,3-butadiene, and 1,3-hexatriene. If you see, the absorption, the maximum wavelength for the absorption increases as the conjugation increases. Like let's say ethene has one pi bond, the maximum absorption is at 174 nanometer. But exactly butadiene has two conjugated pi bonds and absorption is at 217 nanometer maximum wavelength for the absorption, and three conjugated pi bonds, that is 135 hexatriene has three conjugated pi bonds and absorption happens at 258 nanometer. So one more thing, the more the compound is conjugated, it tends to be color. Let's say beta carotene over here, it is highly conjugated compound, it tends to have the color, that is what exactly our carrot color is, the orange color. So this is how the important in the UV region for the absorption is that it has to have the conjugated bonds in its compound. That means it has to have a pi bonding system. That is, it has to be having the pi bonding system or the non-bonding region, so which able to easily go for the electronic transition. Using UV visible spectroscopy or spectrophotometry, we are able to quantify the DNA RNA, at the same time understand its purity. So, as I said, the DNA absorbs at 260 nanometer, which is the nitrogenous bases absorb the UV light at 260 nanometer, because nitrogenous base have the highly conjugated. And here in the protein, let's say the absorption happens at 280 nanometer. I told only three amino acids are able to have the absorption, that is tryptophan, phenylalanine, and the tyrosine. But other than that, our peptide bonds are also able to absorb the UV light. The peptide bonds, which connects the two amino acids or more amino acids together, the peptide bond is also able to absorb the UV light. So now, if we take 260 is to 280 nanometer, where exactly, let's say I have extracted my DNA and I want to check the purity of it. So if the more of the proteins or the, let's say, more of the phenol, the extraction contamination is there, we will be able to analyze by 260 to 280 nanometer in the UV spectroscopy. So that is, if we use the purification measure, that is, it shows the absorbance, that your DNA shows the absorbance at 1.8 to 2.0. If the ratio goes higher than the 2.0, the absorbance goes beyond 2.0, that means your DNA has been contaminated either with the phenol, or also the proteins also might have contaminated. Given the contamination, so it shows the contaminants. Basically, it shows the contaminants. Other than that, if you have enzymes, let's say the prosthetic group, like your cofactors, coenzymes, the prosthetic group, the coenzymes are also able to contribute for the UV absorption. The coenzymes are nothing but the NAD plus, FAD plus, the NADH, FADH. All these are also able to contribute for the UV absorption. If we see the normal table in the colorimetric and UV absorption assays, let's say here I'm taking basically protein. You have colorimetric estimation, that is in the visible region 660, 540, 562, and 595. All of them are having some kind of a reagent to react with and give a color, and then you have to estimate the proteins. Very exactly, without making it to be colored, you can directly estimate in the UV region because of the contribution of the tyrosine and tryptophan in the 278 nanometer, that is, I said approximately 280 nanometer, and peptide bond at 190 nanometer. At the same time, carotenoids also can be directly measured under the UV spectroscopy, that is 420, 450, and 480 nanometer. See, DNA also we can measure at 595 nanometer by diphenylamine method. You're making DNA to react with the diphenylamine and give the 5 absorption at 595 nanometer. Directly, you can see the absorbance of DNA and estimate it at 260 nanometer in the UV region.